Sisters. Got my knockoff docs. The t-shirt under the tank top. The red plaid. This was the outfit I used. To be fair, I was in middle school. So, I was elementary, middle school in the 90s. But yes, this is the outfit I wish I had in the 90s. That I would have 100% stolen from my sister if I could have. 100%.
You were there as if you could have.
Well, we are 8 years apart. When I was in middle school, I could not fit her clothes. Now I steal her stuff all the time when I can.
That is so loud.
To be fair, my daughter also steals my stuff because she can fit my shoes and stuff. So.
I'm an only child, so I don't know how that feels.
I am the youngest of 3, so I don't know how that feels. All right, what we got to do for our K up here? After our minor 90s detour. Ooh, we got to get our K by ourselves, but we don't want to subtract. What do we need to do? Divide. Because they're pressed right against each other, so they're being multiplied, so we need to divide both sides. So our K is going to be -3/24. You can write it like that. It works for the purposes we need. This does simplify. Those are both divisible by 3. These tendrils are going to annoy me all day long. But you can work with it exactly like that if you want to. Because all we need to do is find y if x is -16. So we know our y is going to be that x, -16, times our k. -3/24. You can do it just like this. You type it in the calculator like that, it'll simplify it for you. You could also simplify the k. That would be -1/8.
I'm slow.
It's okay.
This, like, almost concerningly slow.
It's okay. We'll get the brains to boot up. So what do we get for our y here? Type this in the calculator.
That's what I'm about to do.
I know, but you are not the only person in the room.
No.
Is it being annoying?
No.
Wasn't baggy popular in the 90s?
Huh?
Wasn't wearing like super baggy stuff popular in the 90s?
The super like baggy pants started in the 90s, but it really hit its stride in the 2000s. That's when like the sagging, where you could see flesh above the pants. It was a lot.
I got 10. Is it 2?
It is indeed 2. I couldn't hear you. But yeah, it's 2. Same kind of vibe for the next one. The only thing that's different is instead of it being directly across the equal sign, when they're inversely related, they're on the same side. Yes, our y and x are on the same side of the equal sign, and they're going to equal, definitely not another x, they're going to equal k. And again, we have our kind of example piece. We know y equals 5 when x equals 4. So if y is 5 and x is 4, what's k? 20.
Wait, hold on. Oh.
So then we're asked to figure out what y is when x is 2. So we know our y times x should be 20. So we want to know what y is if my x is 2. What's our y going to be? 10.
Whoa.
Good morning, Times High School.
Turn your speaker down and talk faster. Turn your speaker down and talk faster. Page number's correct. Okay.
I'm sorry, but girly pop needs to learn how to do that better.
Girlie, the problem is that she has a speaker in her office and her phone is too close to the speaker to do that. So, because it's getting feedback from the phone from the speaker on the ceiling. So there's very few rooms for which that works well. The announcements.
She does it from her office?
I believe so.
I didn't know you could do that.
There are ways. But they are not commonly known and or used. All right, so we are going to continue working with our relationships here, but we're going to start looking at some story problems and some context stuff.
Ew.
I know.
Wait, it's Wednesday, right?
Today is indeed Wednesday.
Okay. When you get a chance, I would like to pass for
Yes. So we're going to do some story problems today. We'll do some solving tomorrow. Then we'll do a few more story problems on Friday, and then we'll be done for this semester. All right, so we've got up here on page 21. Look at my typed in page numbers are right. What? Oh my gosh. We've got the Kyle mows lawns for $25 each. So if X represents the number of lawns mowed and Y represents the amount of money he makes, then what it means is that the Y varies directly with the X. The amount of money he makes varies directly. So what would this look like as an equation? Ignoring all the other questions, how can I write an equation for Kyle's money that he makes mowing lawns?
It says it's direct.
It is indeed.
So it would be.
Just kind of work with the story. Don't necessarily focus on that. Look at these parts. If Kyle mows lawns for $25 each and X is the number of lawns, Y represents the money he makes. How could we write that as an equation?
Per. I don't know why my brain just wants to do that. It's weird.
Thinking too hard about it. That's okay though. So we know he makes $25 for each lawn. How many lawns is he mowing?
Wait, that would be the value of K.
How many lawns is he mowing?
X.
X. We don't know. So if he makes $25 for every lawn, what do we need to do with the 25 and the X? Do they get added, subtracted, multiplied, or divided? He doesn't have any extra money sitting around that we know of, so the amount of money he has straight up is just going to be whatever this is. So 25X equals Y. This is a direct variation. If I was to put my little direct variation thing we have, that was our Y equals X times K. So what's the value of K here? 25. So when we're writing a function rule, oh wait, we just did. That's this guy. And then we're asked a question, how many lawns did Kyle mow in order to have earned $500? What would we do with that?
Put it in.
For Y. This is a total. It's the amount of money he makes, Y. So we could solve these by looking at 25X when we want to know when it equals the 500.
This is what happens when you say
It does indeed. How many lawns would he have to mow? 20. Bless you. So he would need to mow 20 lawns. So these are linear systems that we've worked with before. It's just using these direct and inverse variation things. So the words on them and reading through it is kind of the big part. So let's look at that's all we need to do for that first one. Let's look at the next one. We've got Wanda sleeps. Children have found that there's an inverse relationship between the number of hours she sleeps and how many times she gets upset. So one night she sleeps for 3 hours and is upset 20 times. And then the next time she's only upset 12 times. And they wonder how much sleep she got. It is. So if we know that there is an inverse relationship here, this one's a little less easy to figure out. If we know there's an inverse relationship, how are we going to kind of set that up?
We set that up by doing y times x equals k.
Equals some number k. What are we going to have y be? What does y stand for in our case? We have two variables here. We need to know what those mean. What's y going to be? What's x going to be? Give me a second. What are the things we're asking about?
How many hours she sleeps and how many times she gets upset.
Hours she sleeps and times she gets upset. Those are the two things we're being asked about. Those are our variables. So one of them is going to be how many hours she sleeps. So I'll go ahead and put that as my y. And the number of times she gets upset is going to be our x. So we need to figure out what that k is. I have a smaller pad, but I have one back here. So see what we can do about substituting in some values. Because we know on one of those days that she slept for 3 hours and was upset 20 times. So the hours of sleep she got, which is our y, was 3. That's not bad. The number of times she was upset was 20. Those are two things that went together. So what is our k here, our constant of variation? 60. That means if I'm looking to make a prediction on what's going to happen with our y times x equals 60, and we know on one set random time she got upset 12 times, that's going to be our x. So we're trying to figure out what y is if I know that x is 12. What is y going to be? How many hours of sleep did she get?
Gonna use my calculator. Don't work. 5.
Yeah. Divide both sides by 12, and we're going to get 5. Questions on this one? What's up? We good? We good? Okay, let's check it.
Wait, I know what's up. Space.
Technically it's out, but that's okay. All right, let's do another one. So we've got an area of a trapezoid varies jointly with its height and the sum of its bases. Thank you. So this one is a little bit weirder because it's not that we just have the height and the base. We have the sum of the bases. Trapezoids have two bases. This trapezoid, that's these guys. So we usually say that this has base number 1 and base number 2. The two bases. So when we say the sum of the bases, what does sum mean when we're looking at stuff like this? Adding. So we take our two bases and we add them together in order for this to be a thing. So the piece that's sum of the bases needs to be those two bases added together. So the purple part is going to be our base number 1 plus that base number 2. That's what those little numbers at the bottom mean. It usually just means number 1 and number 2.
So
If you want to call them. Mm-hmm. Yeah. Because we have 3 pieces up here. We're talking about something being jointly varied. And we've got our area, which is jointly varied, meaning it's across the equal sign from the height. So it's going to have our height. And it's going to have some of those bases. Our base 1 and our base 2. Base 2. And some constant. Okay. So then they're giving us an example so that we can figure out what our base is gonna, or what our K is gonna be with this one. We know an area is 480 square meters when the height is 20 and the two bases are 28 and 20. So filling in all the pieces we get, we have our area of 480. We have our height of 20. And then we need to sum up our bases. Our bases are 28 and 20. So we start by finding all of our pieces and trying to build our equation. And then we're going to substitute all the pieces in that we can. So we'll simplify this in chunks. 480 equals our 20 times 28 plus 20 gives us a 48 times K. So what are we going to get for our K? Yeah. If we multiply those two things together and divide both sides, we actually wind up with 1/2 is that constant of variation, that K. Now that comes up any space to work with here. So then we're asked to figure out what the area of the trapezoid is with this information down here on this very bottom line. So our 8 meters and its bases are 10 and 15. So we're trying to figure out our area if we know that we have 8 meters as height, our bases are 10 and 15, and we know our constant of variation, K, is 1/2. I wrote it over here. It happens. We all do like this. So what are we going to get here? We get 1/2 times 8 times 10 plus 15. So you can think of this as 8 times 25 times 1/2, which is the same thing as 4 times 25, which is the same thing as our 100 square meters. Meters squared. questions on this one?
I wish I had caffeine.
Sorry. Can't help you with that one. All right, the last one we are dealing with is a inverse variation here. So we've got the length of a violin string varies inversely to the frequency of its vibrations. So if the string is 10 inches long, it vibrates at a frequency of 512 cycles per second. So we're asked to find how many cycles per second an 8-inch string is. So we know it varies inversely. What's kind of our basic structure for an inverse variation? Yx equals k. Gorgeous. What's our y going to stand for? We need to pick something for y to be.
The frequency.
You can do that one as its frequency. What is our x going to be then? What's the other piece of information we're working with here? The length. The length of the string. That's why when you push on the string with your fingers and change its length, it changes the note it makes. You're changing the length of the string. So we know our example that we're given, a 10-inch string vibrates at 512. So when we substitute in the length of the string to be 10, and our frequency is 512, we know that's going to equal our k. So what is k going to equal?
Why did I almost put 50 instead of 10?
I don't know.
It's basically the big number with a 0 on it.
Yep, because to times by 10, we just put a 0 on the end, so it's 5,120, which means we know our kind of generic form for these violin strings. Just have to finish that before I went to go grab it from the door. Our kind of generic form of this equation is going to look like this. So find the frequency of an 8-inch string. Get all the way to an answer. Take a couple minutes, get all the way to an answer here. Try it. I'm going to freeze the screen. See what we can come up with for an answer. All right, what did we get? 640 cycles per second. Okay, so working with our variation as it comes to these story problems is really going to set us up for the story problems you deal with after we do our solving stuff. So we're going to do solving stuff with equations tomorrow. You can see that in the next page and a half. Then we're going to go into our last set of story problems, and then we're done with the chapter. That'll be the end of it. So we're rapidly approaching the end here.
No.
And in fact, that's all I've got for you today. So we actually have time where we can work on stuff and ask questions if we got them. I'm going to pass back a little bit of stuff. I don't have tons for you guys to pass back, but I have a little bit. So I'm going to give you guys back the things that I can. Work through stuff, all that jazz. And let me know if you got questions, if you're working on homework on stuff.
And you have questions, but I'm gonna wait for it until you're done.
What's the question? Got like 12 pieces.
Help and help.
What do fractions need to have to be able to add together?
Same dates.
Super close, it's not a big stuff, but the denominator, yeah. So what can I do to change the denominator?
Multiply.
Mm-hmm. By what?
Well, this thing I'm having trouble with.
Google. So let's do it as we had, like we had 1 over, so it's 4 and 1 over x. What does this one have that this one doesn't? So this one we need to x, but I can't just multiply it randomly. Oh, we can do it more.
This is the thing. I know I have to multiply by -4.
By what? Pick up these factors. So
So-
it's not just the -4 that it doesn't have.
So I was right. I just my brain processed it wrong.
So what are you gonna multiply this rate with?
X plus 4.
And I just do one on the bottom like this?
No.
So we can do a function with a 1. So we're gonna multiply this later.
X minus 4.
Yep. So now, okay, remember, treat those like factors and don't multiply out your denominator. Keep it in factor form. Yes, dear. Yes, there you go.
Oh yeah, I need a password. I'm able to cancel these out, right? Or no?
Nope, since we have adding to multiply everybody out, then we can combine our terms. So multiply out your numerator, use the denominator alone, but multiply out your numerator, then we can combine
And
our
then,
terms.
this one.
Mm-hmm.